The quiet hum of the server racks was the only constant companion in Dr. Aris Thorne's office, a low, rhythmic thrumming that resonated through the floorboards and into the very bones of the building. Dust motes danced in the solitary shaft of weak afternoon sunlight that pierced the grimy window, illuminating a chaotic landscape of stacked research papers, forgotten coffee mugs, and an array of flickering monitors displaying intricate cosmic data. What if every path not taken, every choice you didn't make, still plays out in a reality just beyond your perception? Could the deepest quiet of the cosmos whisper secrets from a universe where your greatest sorrow never occurred, offering not escape, but a profound redefinition of existence itself? Aris himself was a figure often lost in this organized disarray, his brow perpetually furrowed, eyes narrowed in concentration, reflecting the blue glow of his screens. His presence, usually intense and focused, now carried an additional weight, a subtle but profound melancholy that had settled upon him like a second skin over the past 2 years. It was a grief, sharp and insistent, that had reshaped his entire world, leaving him with an unyielding drive, a singular, all-consuming obsession, the many worlds interpretation of quantum mechanics. Quantum mechanics, for those unfamiliar, is the fundamental theory describing the behavior of matter and energy at the atomic and subatomic levels. It's a realm where particles can exist in a superposition of states, like a coin spinning in the air, simultaneously heads and tails until measured. This concept of superposition, where outcomes are probabilistic until observation forces a single reality, has led to what is known as the measurement problem, one of quantum mechanics' deepest mysteries. One of its most profound and debated interpretations, specifically addressing this problem, is the many worlds interpretation, or MWI. Imagine, if you will, a single electron. According to MWI, when this electron faces a choice, say, to spin up or spin down, it doesn't just randomly pick one, collapsing its wave function into a single state. Instead, the universe itself, including you, splits. In one new universe, the electron spins up, and you observe it doing so. In another, equally real universe, it spins down, and a different version of you observes that outcome. Every single quantum event, every tiny probabilistic choice, branches reality into an ever-expanding tree of possibilities, avoiding the problematic collapse of the wave function. This isn't just a philosophical idea for Aris. He believes it is a physically real process, one that might leave detectable traces in the grand cosmic tapestry. For Aris, this wasn't merely an abstract theory. It was a profound, almost desperate hope. The idea that every quantum possibility spawns a new universe meant that somewhere, a version of him existed where the personal tragedy that had shattered his life had never occurred, where a different choice, a different turn of events, had led to a different, perhaps happier reality. This thought, while academically fascinating, was also a deeply personal anchor, driving him to prove the physical reality of these parallel worlds. He wasn't seeking to escape his own reality, but rather to understand the fundamental nature of existence itself, to find a pattern in the universe that might, in some abstract way, offer a quiet solace. He spent countless hours, fueled by lukewarm coffee and an almost defiant determination, poring over vast datasets, searching for any anomaly, any whisper that could corroborate his audacious hypothesis. Is true hope a delusion, or a compass pointing towards a hidden truth that conventional science has overlooked? His chosen hunting ground was the cosmic microwave background radiation, often abbreviated as CMB. Think of the CMB as the oldest light in the universe, a faint, uniform glow that permeates all of space. It's a relic from about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light could finally travel freely. Before this time, the universe was an opaque, scorching hot plasma, like a thick fog. When it cooled, it became transparent, and the light from that moment has been traveling across the cosmos ever since, stretched and cooled by the universe's expansion, reaching us today as microwaves. It's essentially a baby picture of the universe, revealing the tiny temperature fluctuations measured in microkelvins that were the seeds of all the galaxies and structures we see today. Scientists have mapped the CMB with incredible precision, using instruments like the WMAP and Planck satellites, creating detailed maps of these ancient ripples, offering a pristine window into the early universe. It was within these meticulously mapped fluctuations of the CMB that Aris began to uncover subtle, anomalous patterns. He wasn't looking for grand, obvious signals, but rather specific statistical deviations, tiny inconsistencies in the distribution of temperature variations that defied the standard cosmological model. He developed custom algorithms, working late into the night. The only sounds the whirring of his computer fans and the distant, muffled city noises outside. He'd feed the massive datasets into his programs, meticulously sifting through terabytes of information, searching for anything that didn't quite fit the expected Gaussian distribution of temperature variations, nor could be attributed to known foreground contaminants like galactic dust or instrumental noise. Weeks bled into months, each day a relentless grind of coding, analysis, and reanalysis. The air in his office often smelled faintly of ozone and stale pizza, a testament to the hours he poured into his work. What if the universe's oldest light holds a secret language only a broken heart could decipher? Initially, these anomalies appeared as faint whispers in the data, statistical outliers that could easily be dismissed as noise, instrument error, or simply random chance. But Aris, with his physicist's intuition honed by years of grappling with the mysteries of quantum reality, felt a growing conviction. He saw patterns in the cold spots and hot spots of the CMB map that didn't seem to correlate with known foreground contaminations or instrumental artifacts. There were regions where the statistical properties of the fluctuations deviated from what the standard model of cosmology predicted, not by a huge margin, but consistently enough to catch his trained eye. Imagine a perfectly smooth speckled surface where suddenly, in certain areas, the speckles seem to align in an unexpected way, or their distribution subtly shifts. These were the faint signatures he suspected of parallel realities, echoes from universes that had branched off from our own, leaving an imprint on the very fabric of space-time, a cosmic whisper of another existence. He considered these anomalies as potential gravitational imprints from other universes, perhaps from regions where our universe's quantum state had diverged from theirs. If a quantum branching event truly means that two new universes form, then perhaps the very act of this separation, this cosmic fission, could leave a tiny, almost imperceptible gravitational ripple. These ripples, immensely faint, might interact with the early universe's plasma, altering the distribution of matter and energy just enough to leave a subtle mark on the CMB as it cooled. He envisioned it like a stone dropped into a pond, sending out ripples, but in this case, the pond was the early universe, and the stone was the quantum branching of reality itself, a momentary burst of energy at the cosmic seams. The magnitude of these effects would be minuscule, requiring extraordinary sensitivity and rigorous statistical analysis to discern them from the background noise inherent in any cosmic measurement. Could the birth of a new reality send a tiny ripple through the cosmic ocean, a whisper of a path untaken? The moment of his first strong conviction arrived on a Tuesday morning, after nearly a year of dedicated solitary work. A new statistical analysis tool he had developed, designed specifically to detect subtle non-Gaussianities in the CMB data. Deviations from the expected smooth, random distribution of temperature variations finally yielded a result that made him freeze. It wasn't just a single outlier, but a coherent set of deviations, a network of interconnected anomalies spanning a specific region of the CMB map, showing a statistical significance that pushed it beyond mere random chance. His heart pounded as he stared at the glowing lines and graphs on his screen. It was like finding a faint, recurring melody in what was supposed to be pure static. He triple-checked his code, re-ran the analysis with different parameters, cross-referenced with raw data from multiple sources. Each time, the patterns persisted, stubbornly asserting their existence. Emboldened by his findings, Aris felt compelled to share his discovery. He meticulously prepared presentations, drafting technical papers filled with complex equations and statistical analyses, eager to engage with his peers. He approached senior colleagues, renowned cosmologists whose opinions carried significant weight within the scientific community. He spoke with passion, detailing his methodology, explaining the theoretical underpinning of the many worlds interpretation, and presenting the compelling data from the cosmic background radiation. He envisioned a lively debate, a rigorous examination of his evidence, and ultimately, a revolutionary shift in understanding. Yet, his initial attempts were met not with excitement, but with a polite yet firm skepticism. The reactions ranged from dismissive hand-waving to thinly veiled condescension. "Interesting statistical quirk, Aris," one esteemed professor remarked, peering over his spectacles. "But the CMB is notoriously noisy. You're likely seeing an artifact of your own analysis, or perhaps some uncatalogued foreground contamination." Another colleague, a brilliant astrophysicist known for her sharp intellect, suggested, "Extraordinary claims, Dr. Thorne, require extraordinary evidence. What you have here, while intriguing, looks suspiciously like wishful thinking, perhaps a projection of your theoretical bias onto the data." The term noise became a recurring refrain, a convenient label to brush aside anything that challenged established paradigms, especially those touching on the controversial measurement problem of quantum mechanics. Aris found himself increasingly isolated. His once eager invitations to collaborate dwindled. Colleagues began to avoid eye contact in the hallways or offered perfunctory nods. The scientific community, by its very nature, is conservative. New ideas, especially those that threaten to upend fundamental understandings of reality, face an immense uphill battle. The many worlds interpretation itself, despite its elegant solution to certain quantum paradoxes, was still considered by many to be a philosophical curiosity, rather than a testable scientific hypothesis. To suggest that its physical manifestations were detectable in the CMB was, in their view, a step too far, bordering on the speculative. Is science truly a pursuit of truth, or sometimes just a defense of established belief? He would retreat to his office, the quiet hum of the servers a constant reminder of his solitary quest. The rejection, while painful, only solidified his resolve. He knew what he had seen in the data. He felt it in his bones, a profound certainty that transcended mere statistics. The faint whispers in the cosmic background radiation were not noise. They were echoes. Echoes from a universe just beyond our perceptual reach. A universe where the choices were different, where the thread of reality had branched. He was convinced that these subtle anomalies, these tiny deviations from expectation, were the first tangible evidence of a grander, infinite tapestry of realities. He needed someone else to see it, someone with an open mind and the observational rigor to validate what his theoretical models and lonely hours of data analysis suggested. His conviction remained unshaken, a quiet fire burning brightly in the face of widespread doubt. The fluorescent hum of the university corridors felt particularly oppressive to Dr. Aris Thorne. Each step echoed his isolation, a stark contrast to the buzzing intellectual life he knew thrived behind closed office doors. He clutched a worn folder, its contents a testament to countless sleepless nights spent sifting through data, and headed towards the domain of Dr. Lena Petrova. Lena was an astrophysicist of formidable reputation, known for her rigorous observational work and an almost surgical precision in data analysis. Her office, unlike Aris's own chaotic space, was rumored to be a sanctuary of order, filled with intricate celestial charts and the quiet whir of high-powered computing equipment. Approaching her door, Aris felt a familiar knot tighten in his stomach, a blend of apprehension and a desperate, almost feverish hope. He knew his claims were extraordinary, bordering on the heretical, and Lena's skepticism would be a formidable barrier. Yet, if anyone could see beyond the initial shock to the underlying patterns, it would be her. In the relentless pursuit of truth, sometimes the most unlikely alliances forge the most profound discoveries. But can two minds, so vastly different, truly see the same impossible truth? He found Lena hunched over a large monitor, a constellation of data points swirling across the screen, a faint scent of ozone and strong coffee hanging in the air. Her brow was furrowed in concentration, her dark hair pulled back in a practical bun. She looked up, her expression shifting from focused intensity to a polite, if somewhat weary, acknowledgement of his presence. Aris explained his findings, starting with the subtle, anomalous patterns he had identified within the cosmic microwave background, CMB, radiation. He detailed the painstaking statistical analysis, the custom algorithms he had developed to filter out not only instrumental noise, but also known astrophysical foregrounds like synchrotron radiation and thermal dust emission, and the persistent faint gravitational echoes that refused to vanish. He spoke with a quiet intensity, his words carefully chosen, trying to convey the undeniable consistency he had unearthed without sounding like a zealot. Lena listened, her gaze occasionally flicking from Aris to the printouts he had laid on her desk. Her initial reaction was, as expected, one of professional reserve, tinged with a healthy dose of skepticism. She questioned his methodology, probed the statistical significance of his anomalies, and suggested alternative, more conventional explanations, instrumentation errors, overlooked astrophysical foregrounds, or even just statistical flukes in vast datasets. The universe was, after all, a noisy place. Aris, however, was prepared. He had anticipated every counter-argument, every skeptical query. He explained how he had cross-referenced his findings with multiple datasets from different missions, how the anomalies persisted across various filtering techniques, and how their statistical significance far exceeded the threshold for mere chance. He showed her not just the CMB data, but also preliminary analyses he had run on publicly available gravitational wave and cosmic ray data, hinting at the same enigmatic whispers. As Aris continued, Lena's posture subtly changed. Her arms, initially crossed, slowly relaxed. Her analytical mind, accustomed to dissecting complex observational data, began to recognize something more than just noise in Aris's meticulously compiled evidence. He had identified faint, unexpected deviations in the fabric of space-time itself. Tiny, persistent ripples that did not align with any known astrophysical phenomenon. For instance, in certain gravitational wave events, the team's analysis showed incredibly subtle, almost imperceptible modulations in the trailing waveforms, as if an external, non-gravitational influence was gently tugging at the edges of the space-time distortion, slightly altering the characteristic chirp of merging black holes in ways inconsistent with general relativity. These were not the dramatic cataclysmic signals of merging black holes or neutron stars, but rather a persistent, almost harmonic background hum that seemed to resonate with the CMB anomalies Aris had first discovered. Furthermore, Aris presented patterns from high-energy cosmic ray data. These particles, traveling across the vastness of space at nearly the speed of light, occasionally exhibited peculiar energy spectra or arrival directions that, when mapped against the CMB and gravitational wave anomalies, showed an uncanny correlation. The idea of countless parallel universes seemed too extravagant, too fantastical, and lacked the intuitive appeal of a single, definite reality. Everett himself, disheartened by the lack of acceptance, eventually left academia to pursue a career in defense analysis. For decades, the many worlds interpretation remained a fringe idea, discussed only by a dedicated few. However, in recent years, the MWI has experienced a remarkable resurgence in popularity. As our understanding of quantum mechanics has deepened, particularly with the development of quantum computing and the theory of decoherence, Everett's elegant, deterministic solution has gained increasing traction. Many physicists now consider it a leading contender, if not the most compelling interpretation of quantum mechanics. It avoids the need for a mysterious collapse mechanism and maintains the unitary smooth evolution of the wave function, which is a desirable feature in theoretical physics. The implications of the many worlds interpretation are profound, challenging our very notions of reality, choice, and even personal identity. If every quantum possibility is realized in some universe, does that mean every decision you've ever contemplated, every path not taken, has been fulfilled by another version of you? Does this vast cosmic branching fundamentally alter what it means to be you? It certainly paints a picture of existence far grander and more complex than we might ever have imagined, suggesting that our universe is not singular, but an infinite, ever-splitting kaleidoscope of realities. What does this mean for our understanding of fate versus free will? We have journeyed into the strange quantum realm, where every choice, every possibility, might lead to a branching of reality, creating countless versions of ourselves existing in parallel universes. That idea, profound as it is, speaks to a multiverse born from the very fabric of observation and quantum uncertainty. But what if the multiverse isn't just a consequence of tiny particles making choices? What if it's an even grander phenomenon, woven into the very origin and evolution of the cosmos itself? Imagine worlds beyond our own, not merely differing by a single quantum flip, but by entirely different fundamental laws, different dimensions, different histories. This brings us to another compelling, yet even more mind-bending pathway to the multiverse, the concept of cosmic bubbles, born from the furious expansion of the early universe. Our current understanding of the universe's origin begins with the Big Bang, a moment roughly 13.8 billion years ago, when all matter and energy we can observe were compressed into an incredibly hot, dense state, expanding rapidly ever since. This model has been remarkably successful, explaining the observed expansion of space, the abundance of light elements like hydrogen and helium, and the existence of the cosmic microwave background radiation, the faint afterglow of the universe's infancy. However, for a long time, the Big Bang model faced some perplexing puzzles. How did the universe become so incredibly smooth and uniform on large scales, despite seemingly disconnected regions? Why does space appear so flat, almost perfectly balanced between collapsing under its own gravity and expanding forever? And where are the exotic particles called magnetic monopoles that the early universe should have produced in abundance? These were significant questions that troubled cosmologists for decades. Then, in the early 1980s, a brilliant solution emerged, proposed by physicist Alan Guth: cosmic inflation. Imagine not just a rapid expansion, but an exponential expansion, a period when the universe grew by an unimaginable factor in an unbelievably short amount of time. Guth suggested that immediately after the Big Bang, in the first fleeting fractions of a second, specifically from about 10 to 36 seconds to 32 seconds after the Big Bang, the universe underwent an extraordinary burst of accelerated growth. During this period, its size increased by a factor of at least 10^26, meaning it expanded from something much smaller than a proton to roughly the size of a grapefruit, almost instantly. This wasn't merely a spreading out of existing space, it was the creation of vast amounts of new space itself, pushing everything apart at speeds far exceeding the speed of light. Not because anything was moving faster than light within space, but because space itself was stretching at an incredible rate. This incredible burst of inflation beautifully resolves the Big Bang's puzzles. The horizon problem disappears because all observable regions of the universe were once in close causal contact before inflation stretched them apart, allowing them to reach a uniform temperature. The flatness problem is solved because inflation effectively flattens any initial curvature of space. Much like blowing up a balloon makes its surface appear flatter and flatter to an observer on its surface, and the magnetic monopoles, they were diluted to such an extent that finding one in our entire observable universe would be virtually impossible. Inflation transforms a chaotic, lumpy early universe into the vast, smooth and flat cosmos we observe today. But this powerful idea, while solving old problems, also opened a door to an even more radical possibility. What if this inflationary process, once started, doesn't simply stop everywhere? This is where André Linde and the concept of eternal inflation enter the picture, taking Guth's groundbreaking idea to its logical and mind-boggling extreme. Inflationary theory posits the existence of a hypothetical inflaton field, a kind of energy field permeating space, which drove this super-rapid expansion. As this field slowly rolls down its energy potential, it drives inflation. However, quantum mechanics, with its inherent uncertainties, plays a crucial role here. Even within this smoothly rolling inflaton field, tiny quantum fluctuations are constantly occurring. Imagine a vast, perfectly calm sea, but with ripples and waves constantly appearing and disappearing on its surface due to microscopic random movements. Most of the time, these fluctuations are small and insignificant, but sometimes in some regions, a quantum fluctuation can be large enough to kick the inflaton field uphill again, even as it tries to roll downhill. When such an energetic quantum fluctuation occurs, it can cause inflation to effectively reignite, in that localized region. Instead of smoothly transitioning to a non-inflating state, this patch of space continues to expand exponentially. It's like a vast, ever-growing foam, where some parts slow down and form stable bubbles. These are new universes like our own, while other parts continue to inflate, stretching space so rapidly that they essentially give birth to more inflating regions. This process is not just continuous, it's eternal. Once inflation begins, it never truly stops everywhere. It might stop in specific patches, forming a bubble universe, but the vast majority of the volume of the inflating space continues to inflate, constantly spawning new bubbles. Our entire observable universe in this view is just one such bubble, one localized region where the inflatant field finally settled down, allowing matter and structure to form. It's an endlessly self-reproducing fractal of universes. Each of these bubble universes would be truly immense, potentially infinite in size, and entirely separate from its neighbors. Imagine our universe as a single, solitary air bubble forming in a vast, endlessly expanding ocean of foam. The foam itself is the inflating space, and the other bubbles are other universes. What makes this concept so compelling and so different from the quantum multiverse is the potential for profound variations between these bubbles. Because the inflatant field can settle down in different ways, or because quantum fluctuations can vary, the fundamental physical constants and laws might be different in each bubble. One universe might have a slightly stronger gravitational force, another a different speed of light, a third might have electrons with a different mass, or even a different number of spatial dimensions than the three we experience, plus time. Some bubbles might be barren, unable to form stars or galaxies, while others might be teeming with life, perhaps even life forms we cannot even begin to imagine based on our own reality. This means our universe, with its specific laws and constants that allow for the formation of complex structures, stars, planets, and ultimately life, is simply one outcome among an infinite multitude. We are not necessarily living in the universe, but our universe, a single bubble in an unimaginably vast cosmic foam. The sheer scale of this idea is difficult to grasp. If you were to travel infinitely far in our own universe, you would still be within just one of these bubbles. The other bubbles are not out there in our space. They are separate, causally disconnected space-time regions, born from the same eternal inflationary process, but evolving independently. There's no way to cross from one bubble to another, no way to peer into their unique realities, at least not with any technology we can currently conceive. So we have two distinct, yet equally profound, theoretical pathways to the multiverse. On one hand, the many worlds interpretation suggests a quantum branching, where every possibility unfolds in its own parallel reality. On the other, eternal inflation offers a cosmological mechanism, where new universe bubbles are continuously birthed from a perpetually inflating space-time. Are these ideas mutually exclusive? Not necessarily. Some scientists suggest they could even complement each other, with each cosmologically distinct bubble universe then undergoing its own quantum branching, leading to an even more complex layered multiverse. The implications are staggering. If there are infinite universes, each with potentially different laws, then what does that say about the uniqueness of our own existence? Does it make our universe less special, or more incredible because we happen to reside in one that can support us? While eternal inflation remains a theoretical framework, it arises from the robust and observationally supported theory of cosmic inflation. The eternal aspect, however, is still debated and relies on specific properties of the inflating field and quantum gravity. Scientists continue to explore the intricate mathematics of these models, seeking potential observational signatures that could hint at the existence of these cosmic bubbles. For now, the idea stands as a powerful, elegant explanation for some of the universe's biggest mysteries, and it profoundly reshapes our understanding of reality, suggesting that the universe we inhabit is but a single thread in an infinite cosmic tapestry. This concept of infinite variation also leads us to consider another profound question. Why are the laws of our universe so perfectly suited for life? Could the multiverse offer an answer to this cosmic lottery? Imagine, if you will, a tranquil, boundless ocean where every ripple and every wave is a universe unto itself. We've journeyed through the perplexing quantum realm, where reality itself seemed to branch with every observation, spawning countless parallel versions of our own world. We've also gazed upon the grand cosmological scale, where the vast tapestry of space-time might be a frothy foam of bubble universes constantly being born from an ever-inflating void. But what if these countless universes weren't just copies, or slightly varied versions of our own, but fundamentally different? What if the very rules governing reality could change from one universe to the next? This question leads us to one of the most profound puzzles in all of science. Why is our universe so perfectly suited for life? Our universe, the one we inhabit and observe, operates under a precise set of fundamental rules, etched into the very fabric of existence. These are not merely the laws of physics, like gravity or electromagnetism, but the specific values that dictate their strength and behavior. We call these physical constants. Numbers like the speed of light in a vacuum, approximately 299,792,458 meters per second. The gravitational constant, a tiny number that determines the pull between any two objects, the mass of an electron or a proton, or the strength of the strong nuclear force which binds atomic nuclei together. These constants are not arbitrary. They possess values that appear astonishingly specific, almost as if tuned with incredible precision. Even a minute deviation in any one of these constants, if it were different by just a hair's breadth, could render our universe utterly sterile, incapable of forming stars, planets, or indeed any form of life as we know it. It's like finding a safe with a million possible combinations, and the very first one you try opens it, revealing a treasure designed just for you. How could such an extraordinary coincidence arise? Doesn't it feel remarkably improbable? Let's consider gravity, for instance. If the gravitational force were even slightly weaker, say by just a tiny fraction of a percent, matter would struggle to clump together. Stars and galaxies might never form, or if they did, they would be far less stable, quickly dispersing into diffuse gas, leaving behind a cold, dark, and empty cosmos. Conversely, if gravity were a little stronger, stars would burn through their nuclear fuel much too rapidly, collapsing into black holes before there was enough time for complex chemistry to evolve, let alone for life to emerge. The delicate balance allows for stars like our Sun to shine for billions of years, providing stable energy for planets like Earth, a crucial timescale for the slow development of biological complexity. Or think about the electromagnetic force, which holds electrons in orbit around atomic nuclei, forming all the atoms that make up everything around us. If this force were significantly stronger, electrons would be pulled much closer to the nucleus, making chemical bonds, the very basis of all biological processes and molecular structures, impossible. atoms would be too tightly bound, unable to interact in the complex ways necessary for life. If it were weaker, electrons would wander too far, unable to form stable atoms at all, leaving a universe without solid matter or chemistry. The precise strength allows for the rich and varied chemistry that underlies everything from water to DNA, enabling the intricate dance of molecules that constitutes life. Then there's the strong nuclear force, the most powerful of the four fundamental forces, responsible for binding protons and neutrons together within an atom's nucleus. If it were just a few percent weaker, atomic nuclei wouldn't be stable. Hydrogen would be the only element in the universe. No carbon, no oxygen, no nitrogen, no iron, no building blocks for planets or the complex organic molecules of life. If it were slightly stronger, hydrogen atoms might fuse too easily, consuming all the universe's hydrogen very early on, preventing the long-lived stars that produce heavier elements through stellar nucleosynthesis. It's a remarkably tightrope walk, isn't it? Just how many such crucial balances are there? And why do they all align perfectly in our universe? Perhaps one of the most striking examples is the cosmological constant, a term in Einstein's equations that represents the energy density of empty space, what we now call dark energy. It drives the accelerating expansion of the universe. Observations tell us its value is incredibly small, yet positive. If it were even slightly larger, the universe would have expanded so rapidly in its infancy that matter could never have clumped together to form galaxies and stars. The cosmic structures we see would simply not exist. If it were negative and sufficiently large, the universe would have quickly collapsed back on itself, long before life could ever have begun. The observed value is so infinitesimally small, differing from theoretical predictions by an astounding 10^120 orders of magnitude, that its existence at precisely this value seems almost miraculous. It's like winning a lottery where the odds are 1 in a number with 120 zeros after it. Such odds defy common sense, prompting deep scientific inquiry. Faced with this astonishing fine-tuning, scientists have pondered deeply. Is it merely an incredible stroke of luck, a truly spectacular cosmic coincidence? Or is there a deeper explanation, something beyond mere chance? One perspective, often called the anthropic principle, suggests that we observe the universe to be fine-tuned, simply because if it weren't, we wouldn't be here to observe it. While undeniably true, this doesn't explain why the universe is fine-tuned in the first place. It merely states a condition for our existence, rather than providing a mechanism for the universe's properties. It feels a bit like saying, the bridge is strong because if it weren't, we wouldn't be standing on it. While true, it doesn't tell us about the engineering of the bridge. This is where the concept of the multiverse, which we explored earlier, offers a truly profound and elegant resolution. If our universe is not the only one, if there are indeed countless, perhaps infinite, other universes out there, then the coincidence of our universe being perfectly suited for life suddenly becomes far less surprising. Imagine an infinite number of universes, each born with a random set of physical constants. In this vast cosmic lottery, it becomes statistically inevitable that some small fraction of these universes would, by chance, possess the right combination of constants to allow for the formation of complex structures, stars, planets, and ultimately, life. Our existence then would not be a miraculous outcome against impossible odds, but rather a simple consequence of probability within an unimaginably vast ensemble of realities. We find ourselves in this particular universe because it is one of the rare ones that can support observers. is like having an infinite number of planets, and we happen to live on the one with breathable air and liquid water. Would you consider that planet a miracle, or simply the only one where you could live? The multiverse suggests that our seemingly unique cosmic home is merely one among an infinite array of possibilities, not necessarily a singularly special creation. But how could these different universes come to have different physical laws and constants? Is there a scientific mechanism that would allow for such variation? Or is this merely wishful thinking? This is where theoretical physics, particularly the ambitious framework known as string theory, steps onto the stage. String theory proposes that the fundamental constituents of the universe are not point-like particles, like electrons or quarks, but tiny, vibrating one-dimensional strings. The way these strings vibrate, much like the different notes produced by a violin string, determines the properties of the particles they represent, and thus, the fundamental forces and constants of nature. It's a vision of reality as a cosmic symphony of vibrating strings. A key feature of string theory is its mathematical requirement for extra spatial dimensions beyond the three we perceive: up, down, left, right, forward, back, and the one dimension of time. These additional dimensions, often hypothesized to be 6 or 7 of them, are thought to be compactified or curled up into incredibly tiny, intricate shapes, far too small for us to detect directly with current technology. Think of a garden hose. From a distance, it looks like a one-dimensional line, but up close, you can see it has a curled up, two-dimensional surface. Similarly, these extra dimensions are theorized to be curled up into incredibly complex, microscopic geometries at every point in space. These curled up dimensions are crucial, as their specific geometry influences the physics we experience. The string theory landscape refers to the unimaginably vast number of ways these extra dimensions can be curled up. Each distinct way of compactifying these extra dimensions corresponds to a different vacuum state of the universe. And each vacuum state, in turn, dictates a unique set of physical laws and values for the fundamental constants that we observe in our familiar 4 dimensions. It's like having an enormous dial with countless settings, and each setting creates a slightly different reality, a unique flavor of physics. The estimated number of these possible vacuum states is truly staggering, often cited as 10⁵. To put that into perspective, the number of atoms in the entire observable universe is roughly 10⁻80. So 10⁵ is a number so vast, it practically beggars the imagination. It means there are more possible configurations of physical laws than there are particles in our entire observable cosmos. What does such an immense number imply for our understanding of reality and the uniqueness of our own physical laws? Now, let's tie this back to the concept of eternal inflation, which we discussed earlier. Recall that eternal inflation suggests our universe is just one bubble in a continuously expanding, self-reproducing multiverse. Within this framework, it's theorized that each new bubble universe, as it emerges from the inflationary foam, could randomly settle into a different one of these 10⁵ possible vacuum states from the string theory landscape. Each bubble could have its own unique set of constants, a slightly different gravitational strength, a different electron mass, a different cosmological constant. In one universe, carbon might not exist. In another, gravity might be so strong that stars collapse instantly. So the process of eternal inflation, combined with the string theory landscape, provides a powerful and elegant mechanism for generating a multiverse where not only do quantum possibilities branch, but where the very fabric of physical law can vary. Our universe, with its perfectly balanced constants, would simply be one of the fortunate outcomes in this grand cosmic experiment, one where carbon-based life could arise and ponder its existence. The apparent fine-tuning then ceases to be a profound mystery demanding a singular explanation, and instead becomes a simple, albeit astonishing, statistical outcome within a cosmic lottery. This cosmic lottery model fundamentally alters our perspective on the universe. It suggests that the specialness of our universe isn't due to divine design or an improbable fluke, but rather a statistical inevitability within a much larger, diverse reality. We are not winners of a truly impossible lottery, but simply inhabitants of one of the winning tickets among an infinite pile of tickets. The universe is fine-tuned for us because we could only exist in a universe that is fine-tuned for us. It shifts the question from why is the universe so perfect to what kinds of universes can support observers. Of course, it's important to remember that both eternal inflation and the string theory landscape are highly theoretical concepts. String theory itself has not yet been experimentally verified, and the landscape is an implication of the theory, not a direct observation. There are scientists who find this multiverse explanation for fine-tuning unsatisfying, arguing that it's a way to explain away a problem by positing unobservable entities. They might ask, why this landscape? Why these probabilities? The debate continues, pushing the boundaries of our understanding and forcing us to confront the limits of current scientific inquiry. Yet, the elegance of this solution, the way it naturally resolves a profound puzzle without invoking supernatural explanations, makes it a compelling area of ongoing research. It provides a framework within which the seemingly miraculous conditions for life in our universe can be understood as a natural consequence of a much grander reality. It invites us to imagine a cosmos far vaster and more varied than we ever conceived, where our universe is but a single fortunate thread in an infinite cosmic tapestry. So the idea of the multiverse, born from the perplexing quantum realm and expanded by the dynamics of cosmic inflation, offers a powerful answer to the question of why our universe seems so uniquely hospitable. It suggests that the precise values of fundamental constants, those numbers governing gravity, electromagnetism, and the very structure of atoms, are not unique to our reality. Instead, they are but one permutation among an infinite array of possibilities realized across countless parallel universes. We are merely the fortunate residents of a universe where the cosmic dice rolled just right for life to emerge. This perspective doesn't diminish our universe's wonder. Rather, it embeds it within an even more astonishing, unimaginably vast tapestry of realities, challenging us to rethink what existence truly means and to consider the profound implications for our own place within this grand cosmic scheme. Imagine for a moment a quiet morning. The sun gently filters through the curtains, and the world outside is just beginning to stir. You stand before your closet, contemplating your choice of attire for the day. A simple, everyday decision, perhaps, yet in the strange landscape of the multiverse, even this seemingly trivial act might hold a profound significance. What if, with every such small choice, every path not taken, every what if that flits across your mind, a new reality unfurls, giving life to all those possibilities? It's a concept that challenges our very understanding of identity and the nature of consequence, suggesting that the you experiencing this moment is just one thread in an unimaginably vast tapestry of realities. We have previously explored the peculiar nature of quantum mechanics, where particles exist in a state of superposition, holding multiple possibilities at once until they are observed. We also delved into the many worlds interpretation proposed by Hugh Everett III, which posits that instead of these possibilities collapsing into a single outcome, the universe simply branches. Every time a quantum event occurs, every measurement is made, the universe splits, creating distinct parallel realities. In one, you might choose the blue shirt. In another, an identical, you chooses the red. Both outcomes are equally real, occurring in separate, causally disconnected universes. And these aren't just grand cosmic events. These branchings are happening constantly, incessantly, at every quantum turn, all around us, and indeed, within us. Consider the sheer dizzying scale of this continuous branching. It doesn't just apply to monumental decisions or distant astronomical phenomena. It permeates every fabric of your existence. Let's take a look at a typical day. You wake up. Perhaps a certain thought crosses your mind, a faint memory, or a fleeting impulse. The precise firing of neurons in your brain is a quantum process, involving the probabilistic tunneling of electrons or the energy states of molecules. According to the many worlds interpretation, these microscopic quantum events, occurring billions of times per second within your own mind and body, trigger countless splits in reality. In one universe, you remember a dream vividly. In another, it fades into obscurity. In one, a random genetic mutation occurs in a single cell, perhaps harmlessly. In another, it does not. These are the infinitesimal, silent branchings that form the bedrock of your personal multiverse. Then, there are the conscious choices, the ones we actively ponder. Will you have coffee or tea this morning? Will you walk to work or take the bus? Perhaps you choose coffee, savoring its bitter warmth. In another universe, an identical version of you, having made the opposite choice, is now enjoying a calming cup of tea. The paths diverge, subtly at first, but irrevocably. Your day unfolds differently in each reality, shaped by that initial, seemingly minor decision. Maybe the person you would have met on the bus, had you taken it, is now meeting a different version of you in that other universe. The possibilities spiral outwards, creating a dense thicket of parallel experiences. Does that mean your choice truly matters if every possibility plays out somewhere? Or does it simply define which specific thread of the tapestry you are currently experiencing? Now, let us consider the more significant crossroads of life, the moments where choices feel weighty and consequential. Imagine a young student deciding on a career path, to pursue a passion for art or to embark on a more stable career in science. In one universe, a version of that student dedicates their life to painting, experiencing the joys and struggles of creative expression. In another, an equally real version of that student becomes a brilliant astrophysicist, unraveling the mysteries of the cosmos. These are not merely hypothetical scenarios. Within the framework of the many worlds interpretation, both lives are being lived out simultaneously by equally real versions of that individual. Every path not taken, every what if that has ever haunted your imagination is not just a fleeting thought, but a concrete reality for a version of you. Think about relationships, for instance. The person you chose to marry, the friend you drifted apart from, the chance encounter that led to a lifelong bond. In an infinite multiverse, there exist universes where you never met your spouse, where you reconciled with that distant friend, where that chance encounter never happened or led to an entirely different outcome. There are versions of you who are single, happily married to someone else, or perhaps pursuing a solitary, adventurous life. These infinite versions of yourself are not merely theoretical constructs. They are as real as the you reading these words right now, each experiencing their own unique, unfolding history, shaped by an endless cascade of choices and quantum events. This concept leads to a profound re-evaluation of personal identity. If an infinite number of you exist, living out every conceivable variation of your life, which one is the real you? The answer, according to this interpretation, is that all of them are. You are not a singular, isolated entity, but rather a collection of experiences distributed across an unimaginably vast number of parallel worlds. Your consciousness, your awareness, is not a fixed point, but rather a multitude of perspectives, each confined to its own branching reality. It's like a colossal tree, with every leaf representing a different version of you, each connected to the same root, yet distinct in its experience of the sun, the wind, and the passage of time. This perspective can be both unsettling and liberating. On one hand, the uniqueness we often attribute to our individual journey might feel diminished. The choices we agonize over, the regrets we carry, the triumphs we celebrate, they are all occurring in some form somewhere else. Does that lessen their significance? Perhaps not. For the you in this particular universe, these choices, these triumphs, and these regrets are profoundly real and consequential. You are still the protagonist of your own story, even if there are infinite other stories being written simultaneously. On the other hand, there is a certain liberation in understanding that every mistake you make, every opportunity missed, is not an absolute final failure. In some other reality, a version of you may have made the right choice, seized that opportunity, or avoided that error. This does not excuse present actions, but it reframes the burden of perfection. It suggests that the totality of your potential is always being explored somewhere across the grand cosmic stage. The universe is not playing favorites with outcomes. It is simply realizing all of them. Imagine the sheer diversity among these infinite versions of you. There might be a version of you who pursued a forgotten childhood dream, becoming a renowned musician or an intrepid explorer. There could be a you who took a different bus one day and met the love of their life, or avoided a critical accident. Perhaps there's a version of you living in a world where a major historical event unfolded differently, leading to a vastly altered society and a unique personal history. The possibilities are not merely endless, they are all realized. Every single quantum permutation, every roll of the cosmic dice finds its expression in a distinct reality. This isn't just about subtle differences in shirt color. It's about fundamentally different life paths, different skills acquired, different people encountered, different worldviews shaped. Your present reality, the one you are experiencing right now, is but one thread in an unimaginably vast tapestry of possible lives. Each thread is woven with the experiences, choices, and quantum outcomes unique to that particular universe. The tapestry itself is not static. It is constantly growing, branching, and expanding with every passing moment, every interaction, every subatomic fluctuation. To truly grasp this scale, consider the sheer number of particles in the observable universe, approximately 10 Cyril 80. Every single one of these particles is subject to quantum probabilities, meaning the number of possible configurations, and thus the number of branching universes, rapidly exceeds any number we can realistically conceive. It's a number so large that it makes the vastness of our own universe seem quaint by comparison. This tapestry is not something you can simply step back and view in its entirety. You are embedded within one specific thread, experiencing its unique journey, unaware of the infinite other threads running parallel to your own. The concept of decoherence, which we discussed earlier, explains why we perceive a single coherent reality. Once two branches of the universe diverge due to a quantum measurement, they effectively become causally disconnected. The information in one branch cannot influence or be perceived by the other. So, while infinite versions of you exist, you remain blissfully, or perhaps frustratingly, unaware of their existence, confined to the narrative of your own specific thread. The idea of infinite selves and branching realities remains a highly debated topic within physics and philosophy. While it offers an elegant solution to some of the deepest paradoxes of quantum mechanics, its implications for personal identity and the nature of reality are profound and continue to be explored. There are no easy answers, and certainly no direct observational evidence that allows us to peek into these other realities. Yet, the mathematical elegance and the philosophical completeness of the many worlds interpretation make it a compelling framework for understanding the universe, and indeed, ourselves. It encourages us to contemplate the richness of existence, not just as a singular predetermined path, but as an infinite exploration of all potential outcomes. Every breath, every thought, every minuscule quantum wobble contributes to this grand, ever-expanding tapestry of realities. You are not just living a life. You are, in a very real sense, living an infinite number of lives, each a unique facet of the boundless potential that is your existence. We have journeyed through some of the most profound and mind-bending ideas in modern science, from the strange dance of particles existing in multiple states at once, to entire universes splitting off with every quantum choice, and even an infinite cosmic foam perpetually birthing new realities. We have considered the possibility that our seemingly perfect universe is but one outcome in a vast cosmic lottery, and that countless versions of ourselves might be living out every conceivable life path in parallel. But now, as we conclude this exploration, a crucial question naturally arises. How do we move from these fascinating theories and elegant mathematical frameworks to verifiable fact? How can humanity ever hope to find evidence of something so profoundly beyond our direct reach? The challenge of observing the multiverse is immense, perhaps the greatest observational hurdle in all of science. Imagine trying to see a light that has never touched your eyes, or hear a sound that has never reached your ears. This is the nature of the difficulty. The parallel universes proposed by the many worlds interpretation are not simply distant galaxies we could one day reach with faster spacecraft. They are causally disconnected realities, separated by the very act of quantum measurement and the process of decoherence. The different branches of reality, once separated, can't interact. Our consciousness, our entire existence, is confined to a single thread within this vast tapestry, unable to perceive the other threads that split off. How then could we ever hope to glimpse them, even indirectly? Similarly, the bubble universes spawned by eternal inflation are often described as being beyond our observable cosmic horizon. Imagine our universe as an expanding bubble in a larger, ever-expanding foam. Light from other bubbles, even if they formed nearby, would simply never have enough time to reach us, even if it traveled for billions of years. The expansion of the space between us and these other universes is so rapid and vast that it effectively isolates them. So, if we cannot directly see or interact with these other realities, does that mean the multiverse must remain forever in the realm of untestable speculation, a beautiful idea with no empirical anchors? Not necessarily. Scientists, ever ingenious, are exploring potential echoes or imprints that might offer tantalizing, albeit indirect, evidence of the multiverse's existence. The most promising avenue for detection currently lies in the cosmic microwave background radiation, often referred to as the CMB. This faint, uniform glow permeates the entire sky, a relic from about 380,000 years after the Big Bang. At that time, the universe had cooled enough for electrons and protons to combine into neutral atoms, allowing light to travel freely for the first time. The CMB is essentially the baby picture of our universe, a snapshot of its earliest moments, preserving subtle temperature fluctuations that represent the seeds of all the galaxies and structures we see today. What kind of echoes might we look for in this ancient light? If our universe is indeed a bubble in a larger, multiversal foam, it is conceivable that it might have, at some point in its history, collided with another bubble universe. Imagine two soap bubbles floating in the air, expanding and occasionally bumping into each other. When they touch, there's a slight distortion, a ripple on their surface. Similarly, if another bubble universe physically collided with our own during its very early inflationary period, this event could have left an observable imprint on the fabric of space-time that would still be visible in the CMB today. Such a collision could manifest as unusual cold spots or hot spots in the CMB map, regions of abnormally low or high temperature that deviate significantly from the expected random distribution of fluctuations. These imprints might also appear as specific patterns. For instance, some theoretical models predict that if our universe has undergone multiple collisions with other bubble universes, or if other universes have passed through ours, they might leave a pattern of concentric circles in the CMB temperature map. These circular features would represent the points of impact and subsequent energy redistribution. The precise shape and size of these circles would depend on the energy of the collision and the properties of the colliding universes. Detecting such a pattern would be a truly monumental discovery, offering a direct window into the multiversal landscape. To search for these subtle signals, scientists have deployed incredibly sensitive instruments. Missions like the COBE, Cosmic Background Explorer, satellite in the early 1990s, followed by the WMAP, Wilkinson Microwave Anisotropy Probe, in the 2000s, and most recently, the Planck satellite, launched by the European Space Agency, have meticulously mapped the CMB across the entire sky with unprecedented precision. These missions have provided us with exquisitely detailed maps of the early universe, allowing cosmologists to search for even the faintest deviations from the standard cosmological model. And indeed, some intriguing anomalies have been found in these CMB maps. For example, there is a large cold spot in the southern hemisphere of the CMB sky, a region significantly colder than statistical models predict. There are also hints of unexpected alignments in the large-scale temperature fluctuations, sometimes referred to as the axis of evil, although this term is more sensational than scientific. These observations are puzzling, as they don't perfectly fit the standard model of cosmology, which predicts a universe that is largely homogeneous and isotropic, meaning it looks the same in all directions and at all places. Could these be the echoes we're looking for, whispers from other realities? It is crucial to emphasize, however, that while these anomalies are intriguing, they are not yet definitive proof of the multiverse. The universe is a vast and complex place, and even seemingly strange patterns can sometimes arise purely by chance, given the sheer amount of data we are analyzing. Cosmologists are actively debating whether these anomalies are truly signatures of new physics, perhaps from a multiversal collision, or simply statistical flukes, or perhaps even subtle foreground contaminations that haven't been fully accounted for. The search for multiple independent lines of evidence is paramount. If we could find similar patterns in different parts of the sky, or using different observational techniques, the case for a multiversal origin would become significantly stronger. Beyond the CMB, other, more speculative avenues of detection are being considered. For example, some theories, particularly those stemming from string theory, propose that our universe is a brane, a three-dimensional membrane, floating in a higher dimensional space, often called the bulk. In this scenario, other brane universes could exist nearby in these extra dimensions. If so, could there be a subtle gravitational interaction between our brane and a neighboring one? Gravity, while the weakest of the fundamental forces, is also the only one that seems to leak into extra dimensions in some models. Perhaps a tiny gravitational pull from a nearby brane could manifest as subtle gravitational waves that we might one day detect, or even slight deviations in gravity's behavior at very small or very large scales. Such findings would not directly show us another universe, but they would reveal the existence of extra dimensions, a key ingredient for many multiverse theories. The realm of particle physics also offers a highly speculative path. If extra dimensions exist, or if there are shadow matter particles that interact only very weakly with our own matter, could experiments at powerful particle accelerators like the Large Hadron Collider, LHC, reveal their presence? While the LHC is primarily designed to probe the fundamental constituents and forces within our universe, some exotic theoretical models predict that collisions at extremely high energies might produce particles that momentarily escape into extra dimensions, or that we might detect the signatures of particles from a dark sector that represents a hidden parallel reality within our own. However, these ideas are far from mainstream evidence for a full-fledged multiverse, and are more geared towards detecting extra dimensions or exotic particles within our own cosmic bubble. The multiverse, therefore, remains a highly debated and largely theoretical concept. Its primary criticism, often voiced by skeptics, is its apparent lack of falsifiability. If a theory cannot be tested or disproven by observation, some argue, then it falls outside the realm of empirical science. However, proponents counter that while direct observation might be impossible, the search for indirect evidence, such as the CMB anomalies, is a scientific endeavor. If we don't find such patterns after exhaustive searching with increasingly precise instruments, it would certainly weaken the case for those specific multiverse models that predict such imprints. Furthermore, many multiverse theories, particularly those derived from cosmic inflation and quantum mechanics, emerge naturally from well-established physical principles that are testable within our own universe. The multiverse, in this view, is not an arbitrary invention, but a logical consequence of our best theories about reality. The ongoing research in cosmology and quantum gravity continues to refine these theories. Scientists are developing new mathematical tools and simulations to better understand what multiversal collisions or quantum branching events might look like, and how their signatures could be disentangled from the noise of our own universe. Future generations of CMB experiments, potentially located in space or on the lunar surface, promise even greater sensitivity, allowing us to probe the early universe with unprecedented detail and perhaps, finally, detect those elusive echoes. Even without definitive proof, the multiverse theory has already had a profound impact on humanity. It has reshaped our understanding of reality, forcing us to reconsider our place in the cosmos. No longer are we necessarily confined to a single, unique universe, but perhaps part of an infinite ensemble. This perspective is humbling, yet also liberating. It provides a potential explanation for the fine-tuning of our universe without resorting to supernatural intervention, suggesting we are simply living in one of the universes where conditions allowed for our existence. It drives fundamental research, pushing the boundaries of physics and inspiring new technological advancements in observational astronomy and particle detection. It fuels our imagination, leading to countless discussions and works of art that explore the philosophical implications of infinite possibilities and infinite versions of ourselves. So where does that leave us? We began by confronting the quantum riddle, where reality itself seemed to split into possibilities. We then explored how Hugh Everett III proposed that all those possibilities are real, each unfolding in its own parallel universe. We ventured further into the realm of cosmic inflation, where Andre Linde and Alan Guth showed us how new bubble universes might perpetually sprout from an eternally expanding space-time. We pondered the cosmic lottery, where our existence might be attributed to the sheer number of universes, each with different physical laws. And we grappled with the profound idea that every choice we make, every quantum fluctuation, could be birthing another version of ourselves in a separate reality. The multiverse remains a grand theoretical framework, a testament to the human intellect's capacity to conceive of realities far beyond our immediate experience. While direct observation of other universes is currently beyond our grasp, the search for indirect evidence continues, pushing the frontiers of cosmology and quantum physics. Will future missions to map the cosmic microwave background reveal clearer, undeniable imprints of other universes? Will advancements in theoretical quantum gravity provide testable predictions that hint at the fabric of multiversal reality? Or will new discoveries within our own universe offer alternative explanations for the anomalies we observe? Perhaps we will never definitively see another universe in the conventional sense, but the very contemplation of the multiverse has already expanded our minds, reshaped our understanding of reality, and deepened our appreciation for the vast, mysterious cosmos we inhabit. It reminds us that our universe, vast and wonderful as it is, might just be one thread in an unimaginably grander tapestry of existence. The journey of scientific discovery is an ongoing one, and the possibility of other realities, other versions of you, and an infinite cosmic tapestry remains one of the most exciting and profound open questions at the very edge of human knowledge.